Great, another nice morning, lovely morning in Sydney. I actually had yesterday in Newcastle, which again was very, very beautiful. Let me begin by acknowledging the traditional custodians of the lands on which we are gathered today, the Gadigal people of the Eora Nation, and pay my respects to their elders past, present, and emerging. It is my super pleasure to welcome Ben Eggleton as the speaker today. Ben and I have known each other since we had nice hair and things like that, right? And young children and things like that. So at least, I think, 25 years, order of magnitude. We've been colleagues at the University of Sydney. We both together ran Centres of Excellence at the same time. We were both Federation Fellows at the same time. And I think we both also gave talks at this event of such a long time ago. I think there was only 20 people in the room. That shows you how long ago it was. So Ben has done many, many things. He is a world expert in photonics. He did his PhD here at Sydney, but he went and spent a significant amount of time at Bell Labs, which is kind of the home, the world home of communications, at a time when I think Bell Labs was still doing serious research. He came back here to found a great photonics centre at the University of Sydney, and also the Nano Centre and a whole range of other really fantastic work that's going on at Sydney University and in general with partners at ANU, partners at UNSW and so on. He also, came to prominence under my predecessor, Mary O'Kane, who said, we need a network in sensing. We need a network so that we can bring together the experts in sensing, because I have problems like finding koalas and sensing things that all governments need to know and would like to be able to know. So Ben was the founder of our first research network, and the research networks have been a really great thing that my office has run. We've got 3-4 networks now. We've had other ones as well, and they really bring together the community, all the universities, all the researchers. They help solve problems in a range of different areas which are of interest, not just to government, but to industry. And I will say the sensing network that we've had has been one of the most successful networks we've ever had. In fact, we still fund it today, and it still has the same leadership, and it has been really wonderful in terms of what it does. And so we're going to hear quite a bit about that today when Ben talks. But let me just say a few other things. He is a really distinguished researcher over many, many years, fellow of the IEEE, fellow of the Academy of Science, a double Federation Fellowship. Did you also get a Laureate Fellowship? Yep, you got a Laureate Fellowship as well, 2 Centres of Excellence, ... Too many things, basically. And of course, is now also significantly involved in the defence industry and the sensing needs and everything else going on there. So hopefully we're going to hear many things about that today. So as I said, it's my pleasure to welcome Ben to the stage today. Thank you very much.
Thank you, Hugh, for that wonderful introduction. And thank you for being here, Hugh, because I know you were in Newcastle and, as I understand, got the train down last night so that you could be at this event. I've been looking forward to this for a long time and excited to be with you to take you on a bit of a journey over the next 45 minutes. I want to acknowledge that we're on the lands of Gadigal people of the Eora Nation and pay respect to elders past, present and emerging. And I guess we're all familiar with sensors. I think you all kind of get the sensor as a concept, but I hope that over the next 40 minutes, I'll be talking through the concept of a smart sensor. And I'm going to take you on a bit of a journey in terms of why they are absolutely key to New South Wales and the nation. And that infographic on the front slide there is kind of pretty dramatic, but I'll come back to that and give you a bit more context. But I guess just in terms of setting the scene, a bit of drama, a bit of a sort of what's played out recently. You've all been probably tracking Artemis 2. What a great heroic milestone for humankind to go again out around the moon. I guess what I've heard stated is that Artemis 2 was less a flag-planting mission. In fact, it didn't plant a flag, rather a flying testbed for next-generation sensing. And so Artemis 2 was loaded with advanced smart sensors inside to keep the astronauts healthy, outside to measure radiation to provide navigation. So really great example, and I think this will come to life in the next 45 minutes. But the smartphone that you have with you also has many of those sensors embedded in it. So I guess the theme of this discussion is that smart sensors are part of our lives today. They are essential to security, to productivity, to health, and New South Wales, Australia has some really world-class research that I'll be speaking to. So on that note, let me take you to a bit more specificity. Underpinning the smart sensors and underpinning the research that I'll be talking to today, semiconductor chips. Now, again, semiconductor chips are part of your world. Everyone probably has a smartphone. I picked up recently the iPhone 17, I think it's the latest version. I spent 3 days syncing with my existing phone. Eventually, I'll be able to take it home. But the iPhone 17 has a chip embedded in it, and that chip is a semiconductor chip, and there are probably 25 billion transistors on that chip. Okay, and I'll come back to that. I'll elaborate on that because the semiconductor chip and the processing power associated with semiconductors is underpinning the smart sensing narrative. And at the same time, it is the platform that photonics, the science of light, that I'll be elaborating on, is anchored on. The right-hand side there is a photo of a photonic chip sitting on a 50-cent coin. And that is a light chip. It's not a semiconductor electronic chip, it's a photonic chip. So this is really the narrative for my presentation. So what am I going to cover today? Well, I'm going to start with a bit of scene setting context, global, national, and local. I think it's fair to say we are living in really interesting times, unprecedented times, and as I will elaborate on, the global context is putting pressure on the national context, and the universities and New South Wales are responding really well. I'll then dive into smart sensing. I'll elaborate on smart sensors. I'll give it more definition, and I'll speak to a really important concept, that is situational awareness. Situational awareness is what smart sensors enable. I'll then speak to photonics, my research, my journey, and I'll talk through a couple of examples of photonic-enabled smart sensors, and then we'll talk about translation and impact. And as Hugh alluded to, in the New South Wales context, the New South Wales Smart Sensing Network is the vehicle for translating smart sensing innovation from universities into impact. And then at a national level, we have the Jericho Smart Sensing Lab, sponsored by the Royal Australian Air Force. Now, I'm not going to be able to say too much about the details of what plays out in that lab for obvious reasons, but I'll give you some context and I'll give you a bit of a flavour of why it's important for our national security, for our sovereignty. Okay, so let's set the scene. As I said, we are living in really interesting times, unprecedented times, I would put to you. Global challenges that we haven't confronted since World War II. Sustainability, climate change, there is recognition of climate change. It is real, it is playing out in our world. There is a technology race, and we have the geopolitical context that I don't need to elaborate on because it plays out in the media every day in Europe, in the Middle East. That global context is putting enormous pressure on the national context that is also playing out in the media every day. Key things to highlight: an increased emphasis on sovereignty, sovereign capability, manufacturing, in a way that I think we haven't had since World War II. In that context, there are significant national and New South Wales policies that speak to, for example, future made in Australia. We had the recent announcement of the strategic examination of R&D. I'll come back to that. At a New South Wales level, we have had for many years an innovation framework, great chief scientists and previous chief scientists, as you've heard Hugh speak to, significant prioritisation around industrial, technological capability, semiconductors. Got Stephen Bartlett here Quantum Australia, and of course, national defence, national security, national resilience. And I'll come back to that in terms of the recent announcement of the updated National Defence Strategy. Now, that's all pretty serious, isn't it? The good news is, at a local level, the universities, the New South Wales government, and I think it's fair to say the Commonwealth are working together really well to accelerate capability and innovation. And there are lots of different vehicles. Hugh has spoken to the innovation networks that have been very successful in New South Wales. At a Commonwealth level, a lot to be said. Quantum Australia is an exemplar. I'm going to speak to really three specific initiatives. My labs sit in the Nano Institute at the University of Sydney, who alluded to state-of-the-art research infrastructure that supports high-performance labs. The director of Sydney Nano is in the audience. The Semiconductor Sector Service Bureau that speaks to semiconductors that I've alluded to, an important vehicle for accelerating semiconductors. The NSSN I'll come back to, and then the Jericho Smart Sensing Lab, again, a Commonwealth-sponsored initiative to accelerate smart sensors for national security. So that's the global context, that's the national context. This is serious stuff. There's good things happening in Sydney, in New South Wales, in Australia. Let me unpack. So, the world is becoming increasingly complex. I think that is clear, and we are increasingly blind without sensing systems. And so I'm going to speak to situational awareness. So this is a concept that arguably goes back to the early days of robotics, and I feel humble sitting 1.5 meters away from Hugh because Hugh was talking about these types of concepts before I was in this business. But it's fair to say situational awareness and sensor fusion, that I will elaborate on, has been around since the early days of robotics, but it has come back in a serious way, enabled by the advanced compute that semiconductor chips are providing and photonics. So what is situational awareness, and why have I got this dramatic infographic on the slide of Australia? It appears to be burning. It was an image created by AI. I acknowledge that I literally went to Copilot. I said, please create an image that represents what I hope to speak to at the New South Wales Parliament Science and Breakfast Lecture, and that's what it created. So there you go, Hugh, AI in action. Situational awareness speaks to three constructs. Perception, we need to detect and recognise elements within our environment. We need to understand the meaning and significance of what is perceived, and we need to anticipate future states and act before threats materialise. Okay, that's a bit abstract. Let me turn that into a physical embodiment. Well, the sensors are the building blocks to achieve that situational awareness. Now, everyone, as I said, has a whole bunch of sensors embedded in their smartphone. My Fitbit, I'm pretty fixated on data and metrics with everything I do, and I've got colleagues from my University of Sydney research operations role who know that. KPI, metrics-driven person. So sensors, simply speaking, convert physical world measurements to electrical output. So again, sensors sit in your phone. But a smart sensor is a more sophisticated construct. A smart sensor speaks to a sensor where we've added connectivity. That sensor is connected to the cloud. Maybe that sensor has some edge compute embedded on it. That means there's computational power sitting on the phone or the Fitbit. Maybe some storage. There's fusion. We'll talk about what that means with other sensors. But importantly, AI to provide some type of synthesis that is the basis of that situational awareness. Now, some of you might be thinking, well, it sounds a little bit like Internet of Things, which was a construct that goes back 10, 15 years. Not quite, but it's similar to the idea of creating an Internet of Things, an Internet of devices that are connected, that sense, but it's really that the AI provides that situational awareness that informs some type of operator or end user what action to take, how to respond to that particular environmental perturbation or effect. Okay, so a little bit deeper. To take it to the next level, a bit more sophisticated explanation, this is the idea of sensor fusion. Now, Sensor fusion, as per the word fusion, literally speaks to combination of data from multiple sensors to create a more accurate and more complete and more trusted picture of what is happening. It's one thing to rely on just one sensor to measure my pulse rate, the temperature. If I really want to understand my environment, to anticipate future, to synthesize, comprehend, I'm needing multiple sensors and some type of intelligence, human intelligence or digital intelligence, which is the idea of AI. Why it matters? Well, simply speaking, individual sensors will see fragments of the world. Fusion integrates, cross-checks and complements those views, reduces uncertainty and fewer blind spots. Fundamentally, sensor fusion delivers actionable information to the end user operator. Okay, so this is the abstract kind of background tutorial framing for smart sensors. And now we're going to go into a little bit more depth and detail. For those that might have struggled a little bit with that explanation, it turns out sensor fusion is actually embedded in our world and our existence. We are actually great examples of sensor fusion in that the way we see, the way we hear, that is sensor fusion. Okay, so our vision assists our hearing. Okay, these are two senses that work together, and we actually have intelligence. We are intelligent, so we don't need edge compute because it's sitting here, and hearing can assist seeing. So when you go home and you're thinking about this presentation and struggling with some of these constructs, sensor fusion, I'd love it if you could play back this very simple understanding that the human is a sensor fusion device. The other example, of course, is autonomous vehicles. Now, they're a great example. What's been playing out over the last 5 to 10 years, exemplified by the Tesla, Elon Musk's vision. He's got very strong opinions on what sensors are needed. He's been very negative on LiDAR, for example. I'll elaborate on that. He speaks very passionately about computer vision. He says the human is a sensor fusion system. We rely on simple cameras. We do pretty well. So the Tesla is actually a pretty simple example. So here again, even my Honda has some pretty good sensor capability built into it. It probably doesn't have the advanced AI and situational awareness that the Tesla has, but it incorporates a whole bunch of sensors that provide some level of enhanced driving, not quite autonomous driving, but I think you understand, again, what I am speaking to. Okay, now, just to go back to the semiconductor chip, because it's important to really understand that the incredible progress and the timeliness of smart sensors as a paradigm, as a campaign that we have championed in New South Wales is underpinned by the breathtaking progress in compute over the last 50, 60 years. And that's best represented by the well-known Moore's Law. Moore's Law simply speaks to a prediction that Gordon Moore made early on in the history of electronics, that the density of microchips in terms of the number of transistors that could be embedded on a chip would increase at the same rate, roughly speaking, double every year, and that has exactly happened. And so, as I said, semiconductor chips today, the iPhone 17 probably has 25 to 50 billion transistors. That's more computational power than the entire space shuttle had. And that edge compute is giving us the ability to synthesize in real time to do that compute that is needed to provide that situational awareness. So embedded sensors are everywhere. Data processing can be performed in real time. AI, machine learning, can now be performed on the edge. We have massive connectivity. And by the way, the semiconductor chip, as I will elaborate on, will become a platform for photonics. And photonics is actually the key to the sensing that is needed. So let me come back to that. Right, so technology now is tackling many of the world's greatest problems. And we could speak for hours I'm going to focus on a particular subset, but I know, Hugh, you've probably come back from a conversation in Newcastle that spoke to climate change related, decarbonisation, energy. We know that sensors are playing a big role in terms of atmospheric measurements, ocean health, wildlife monitoring. We'll come back to that. Sensors, smart sensors playing a critical role in the energy domain in terms of critical minerals, infrastructure, smart homes for optimising energy demand consumption. I'm going to speak to pretty obliquely, if you like, defence and national security, but I think it'll become self-evident in terms of threat detection, logistics, rescue and recovery, and then, of course, in healthcare, smart sensors are playing an enormous role. I mean, think about the wearables, think about the sensors that are used in the hospital by the surgeon that I will elaborate on and we could talk through for many hours. In fact, the New South Wales Smart Sensing Network has played a really key role in promoting and engaging across the health sector smart sensors in a number of important use cases, and we'll follow up on that. So that's all a bit of context. Hugh says, you know, we've got to go into the science, let's go into the physics a bit. I know the audience is pretty broad, but I want to bring it back to the science. Every sensor uses a force of physics to interact with the world. I'm a physicist, I'm trained in the physics of optics and photonics, and it turns out that the electromagnetic waved light-based interactions remains one of the most versatile sensing methods, and I'll kind of talk you through that. Best examples, as already spoken to, autonomous driving relies on LiDAR. LiDAR essentially is lasers that scan the three-dimensional environment. That's a photonic sensor. As I said, Elon Musk wasn't a big fan of LiDAR. He relies on computer vision. Well, that's kind of a camera. That's an optoelectronic device. Radar, we're all familiar with radar. That relies on electromagnetic waves. And I'll talk to a photonic enhanced wave radar system. It's all governed by Maxwell's equations. It's all part of the electromagnetic spectrum. It's a pretty dense slide. I'm not expecting you to understand that detailed slide, but just to make the point that light is electromagnetic wave, radar is electromagnetic wave, and the spectrum of electromagnetic wave goes all the way from X-rays through light, infrared, up into radar and millimetre waves. And as a physicist, of course, this is all governed by those beautiful equations, Maxwell's equations, that describe how light, a wave, interacts with the world. And those equations were put forward in 1870. Remarkable. Before the invention of the laser, before we appreciated that the world was quantum mechanical, these equations were put forward by Maxwell. And they are still today absolutely the foundation of all light-based technologies and electromagnetic technologies. So photonics is a key field that continues to explore new sensing possibilities, and it turns out it has been my research area for the last 30 years. So let's go into a little bit more of my background and tell you my story and how I've been thinking about this for a long time. It's not just come together in the last couple of years. This has been a career journey that started back as a PhD student at Sydney. So here's my story. There's a photo on the top left of myself and a former colleague. You might be challenged with which one is me. Is it the taller gentleman or the shorter gentleman? Can anyone guess? The short one, it's the tall one. The short one is Patrice. He was the master's student from France who was visiting in my lab. But that was in the basement of the Madsen building in 1993. And we were doing some actual pioneering experiments on the first fibre optic grating devices in Australia, and that was really trailblazing work that we did and published, and we had a great time, and I graduated in 96. And then, as Hugh mentioned, I spent 7 glorious years in New Jersey, Bell Labs. That's Murray Hill, still there. It's now the headquarters for Nokia. My stock options and residual stock and residual 401k plan sits with Nokia. Got married, Susan, who's in the audience, in Manhattan. and spent 6, 7 years, 2 kids born in New Jersey, and did a lot of work that was at the interface of science and the industry. I was involved in inventing and commercialising technology that ultimately got productised by Lucent, that was the basis of long-haul communications, and that is the backbone of the internet. Came back to Sydney, set up a centre in the School of Physics, a photonics centre that became the national centre for 15 years, created capacity across 7, 8 universities, spin-off companies, and importantly, lots of new infrastructure. Started to get recognised for my leadership. What was I thinking? Should have stayed in the lab. And along the way, with others, we put forward the vision for the City Nanoscience Hub, state-of-the-art science infrastructure on campus that now houses our labs, the labs that the research group that I lead works in, and these are fantastic labs, fantastic facilities. And I served as director for about 5 years. A lot of stakeholder engagement. That's a great photo that I took. I love my selfies. And I do need to remember to take a selfie with this audience in the background, but that's a photo down at Parliament House. You might recognise who's in that photo. Hugh, you're not in that photo. You should have been. We've got Tanya Munro, the Chief Defence Scientist. We've got Paul Scully Power, who I expected to be here today, Australia's first man in space, and first man with a beard in space. And who's that other guy? Our former Prime Minister. And that was just an opportunistic chance to get that great photo. And then I have been serving as Pro Vice Chancellor, which is a great honour and privilege to represent and lead the university's research operations to really accelerate research for impact that addresses the greatest challenges for the common good. And then the Jericho Smart Sensing Lab was established, and I wanted just to acknowledge my team. Some of them are here. This is the photo of us in Canberra a few years ago at the Defence Industry Awards, and I was receiving an award on behalf of the team for the Jericho Smart Sensing Lab that I'll be speaking to in this presentation. So, you might be struggling, what is photonics? I've sort of alluded to it, the science and technology of light. I need to go into a little bit more detail because I do want you to go away and think that photonics is a really important part of our world and understand a little bit about the science and technology. But it powers everything from fibre optics, advanced sensors, clearly, lasers, semiconductor lithography. In fact, the semiconductor chips that are in your smartphones are fabricated using lasers and photonic systems. The term photonics was born shortly after the invention of the laser, and I think it's fair to say it was envisioning photonics as to optics, what electronics is to electrical engineering. Okay, so it's a relatively new construct. I was at Bell Labs in the 90s, and I was in the optical physics department, and it was sensitive to be not the physical optics department. It was different. Physical optics and optical physics were different. And then there was photonics, and photonics is sort of a more modern version of optical physics, but it really does sort of invoke, in the way that electronics speaks to electrons and information, photonics speaks to lasers and information. So, of course, we all understand electronics because it is the basis of computers and compute underpinned by electrons. And again, as I've spoken to a few times, the semiconductor chips have this breathtaking computational power. Well, of course, photonics is the control and manipulation of light. It is the backbone of high-speed communications, and as I said, sensing, and was born with the invention of the laser. And as I've elaborated on, is governed by Maxwell's equations. In the national context, photonics underpins our internet. It is the basis of all connectivity, whether that is connectivity between Australia and the rest of the world, and then connectivity between Sydney and Melbourne. It is all connected by fibre optics, and we all are probably familiar with the National Broadband Network that was established about 15 years ago to really accelerate the Australian fibre optic network. And there's a little cartoon here that actually, it's a bit of fun, but This is serious business. We rolled out these fibre optic cables, and I was at Bell Labs, and Bell Labs Lucent sold fibre, and we work with the companies that deployed fibre, both the transoceanic and terrestrial, and indeed sharks. Not only is sharks, a challenge in terms of Sydney Harbour after rain, but sharks can actually be a real concern for these cables. Anyway, that's just a bit of fun, but that's actually real footage of a shark going up, sniffing around and saying, what's this? Oh my golly, there you go, we've just lost connectivity with the rest of the world. Photonics is a huge part of our ecosystem. This is well established. It doesn't feature as prominently in the headlines as it did 25 years ago, simply speaking because it's embedded in our industries. It underpins connectivity, bandwidth, internet, e-economy, e-health. It is a vital part. In fact, it is the linchpin of probably more than $10 trillion of our economy. $10 trillion of our economy is underpinned by photonics. If you had no photonics, you have no connectivity, you have no prospect for AI, you have no prospect for all of those applications that our society relies on. The actual photonic core industry is about 345 billion. In Australia, 5 billion. It's pretty modest. We can probably lift our game. Millions of jobs, and it's growing. Okay, so I think working with Hugh and others, we've really been promoting that agenda and to really strengthen our manufacturing base and our industrial base. And I think there's more work to do on that front. But I think we are really well placed in terms of being an innovation powerhouse. Right, we're halfway in. So I've covered, 60%. We've covered a lot of ground. I wanted to now get into some examples, but I wanted to wake you up. So I've got a cane toad. How does a cane toad feature in a story about photonic sensors? This is the cane toad that was in my lab. Nuisance animals, ugly animals, really ugly animals. Well, we published a couple of years ago a device that can remotely monitor your breathing. And we tested it on cane toads, and this got picked up in the media. It was patented. We have spun off a company. We've worked with end users, and I'll give you a kind of glimpse. This is a photonic radar system. Unfortunately, the media and many of my colleagues genuinely thought we were solving the cane toad problem. And I want to be clear, we are not saving New South Wales from cane toad invasion. The cane toad is a proxy for a human. So let me unpack that. Well, vital signs, we're all understanding vital signs. Okay, that's your breathing, that's your heartbeat, that's your blood pressure. I can go on and on. Vital signs are clinical measurements that reflect essential body functions. Wearables, great stuff, but I know many of you won't be wearing a wearable. Some of you don't like wearables, and there are many use cases where wearables are not allowed. Or simply speaking, don't really fit for purpose. Think about intensive care units, think about burns victims, think about corrective services. And we had the pleasure of a tour of the Silverwater Maximum Security Prison. Wearables probably not going to go down well in that context for obvious reasons. So we put forward a remote sensing technology based on photonic radar. It's a little complicated, so let me talk you through this idea. Well, radar, as you're familiar with at the airport, is a sensor. It detects aeroplanes, it tells you where they are. Wideband radar, where the frequency range is really, really wide, is more accurate. It can tell you how big the plane is. It can tell you what type of plane it is. But it turns out electronics struggles to generate such wideband waveforms. So we use photonics to create wideband, high-resolution radar that allows for remote sensing. What does that look like? Well, very simply speaking, this is a sensor the size of my smartphone sitting on the wall, in your bedroom, in the hospital, in the clinic, that bathes you with very low intensity millimeter wave radar signals, and it detects locally your breathing and your heartbeat. Okay, that's pretty interesting for a number of reasons. That was published in Nature Photonics. The title speaks for itself, Photonic Radar for Contactless Vital Detection. We were fortunate to secure some funding through the very, very successful New South Wales Government SBIR scheme that invested in pilot projects that led to the formation of a company and some proof of concept. So you can see now the measurements in the lab of the breathing of the cane toad. And the bottom right-hand side is work undertaken as part of that pilot with the SBIR project. I'm just waiting for that animation to load. And that shows you the actual mannequin in the lab that we've set up. And we're simulating breathing, and we're using a sensor fusion modality to actually detect the thermal signature of the human so that we know when we're tracking their breathing, their vital signs. If the person moves around, it turns out the sensor gets a bit confused. And so we're using a sensor fusion modality to really reduce what would be false alarm measurements. Again, take you through that animation. So that was a really successful engagement, and it's ongoing work. Got picked up on Channel 9. I remember sitting there in my house with my family waiting to get through 35 minutes of Channel 9 news to get to the end. A lot of sport, a lot of ads. Very frustrating, but we got there in the end, and there was a great 3-minute story of my team in the labs, and you can actually look at that on YouTube. So that gives you one example. I could talk for hours about other sensor modalities. We've just spoken to photonic radar, useful for vital sign, but also useful for drone detection. So there's a picture of a drone in the lab. I won't go into details. We can pick up the drone propeller blades, obvious use cases, pretty relevant to what's playing out around the world. Won't go into too much detail. We've played into other sensing modalities. This is an example of a neuromorphic sensor. It's an event-based sensor that sees events. It's an abstract idea, but essentially it only sees an event. If it's a stationary situation, it generates no data. Great for picking out particular events. And this is work with our colleagues at the University of Adelaide on sperm tracking. I never imagined that would be something I would contribute to. But we did robustly and accurately track sperm through a microscope, and that contributes to fertility, a big part of our world's challenges. And then we also do a lot of work on acoustic sensors. I won't go into the details, but it's fair to say light is a wave governed by Maxwell's equations. Sound is not light, but it's also a wave governed by an equation that's not too dissimilar to Maxwell's equations. So the intuition that we have for light maps beautifully onto sound waves, and so we've been able to develop and invent some pretty sophisticated acoustic sensors for a range of different use cases. Right, okay, so 3/4 of the way through, Hugh. I want to go a little bit deeper, and I want to talk us through now photonic chips. So I've talked about photonics and I've talked about semiconductor chips. I want to bring those two ideas together a little bit more precisely and explicitly. But to start with, I want to go back to electronics, and I want to introduce a bit of jargon and an acronym, CMOS. It stands for complementary metal oxide semiconductor, right? It's a term that you'll never have to think about again, most likely, but it is an acronym that speaks to how the world's semiconductor chips are manufactured. I always like to think that CMOS stands for cheap because it's made of silicon. Remember that, cheap because it's made of silicon. Now, as I've said a couple of times, breathtaking computational power. We can leverage that same silicon for photonics. Turns out we can print into the same silicon a photonic circuit. So we can take these photonic systems that might be tabletop size and print them onto a chip thumbnail size to massively reduce the size, the weight, and the power. Now, companies have been doing this for a long time. Intel introduced a photonic transceiver about 10 years ago. So this is an interface between Ethernet and photonics. Embedded in that little diddle device, the size of my thumbnail, is a photonic chip, okay, that's helping to modulate the electrical onto the optical. And so photonic chips are the basis of faster, smarter, more efficient technology, and they're having impact across a whole range of areas that we could speak to in healthcare, in environmental monitoring, in microwave communications, and in quantum technology. And I'll just highlight in quantum technology, in quantum computing in particular, Quantum, big company in the news, led by an Australian, still based in the US, but has a big presence in Australia, anchored in silicon photonics. Their whole algorithm architecture is anchored in silicon photonics. That's how they're doing their quantum computing. Photonics is also accelerating AI. NVIDIA is getting on board with photonics. Recently, I don't know if that animation, did that play? I'll do it again. So it is mainstream. It is increasing capacity, bandwidth. It is enhancing compute. It is relevant to quantum. It's also relevant to microwave radar and those other important use cases. Right, so a lot to unpack. Let's see, that's going to finish. There you go. Right, so that really speaks to from the lab to the chip. So this is a cartoon, but it's actually exactly what plays out in our lab. The left-hand side is the lab experiment. Hundreds of kilograms of equipment, lasers, modulators, mirrors, lenses, spectrum analyzers, all this stuff that is the bread and butter of an optical physicist, a photonics researcher. All of those components can be, or many of those components, most of those components can be printed onto a chip the size of your thumbnail. That is breathtaking. And without going into too much detail, you can imagine, I hope, why the Royal Australian Air Force is so deeply invested in that capability. Right, so just to kind of give you a bit of a snapshot of what it looks like, we anchor our technology on silicon. We develop heterogeneous silicon, which means that we blend other materials with silicon. Let's see if that animation is going to work. I might start to accelerate. There's a nice little animation here that kind of gives you a bit of a visualization of what's actually playing out on that chip. It's pretty sophisticated, hybrid circuit with a little bit of electronics to interface with analog, photonic circuitry. The interface between the RF and the optical is all sitting in there. And this work is patented, it is published, and it is the basis of some pretty advanced functionality that you won't necessarily grasp in this session, that rapid fire session, but it is underpinning many of the functionalities that we're delivering, particularly to our stakeholders in Canberra. So photonic chiplets has become quite a trendy term. The term chiplet speaks to this idea that we are anchoring in silicon, cheap because it's made of silicon, CMOS as I spoke to, but we're actually depositing, integrating other materials onto the silicon platform. And this actually is work that has been going on for many years. We started a conversation with Hugh about 6 years ago that led to this Australian semiconductor sector study. And we've been actively promoting these ideas. In fact, it was picked up in the media as Lego-like assembly, this chiplet manufacturing, underpin the basis of the Semiconductor Sector Service Bureau, which has become a very successful New South Wales government-sponsored unincorporated joint venture to promote semiconductors. We have now national reports, and excitingly in Western Sydney, and I'll be there on Friday morning at the Advanced Manufacturing Readiness Facility, there's some capability coming online that provide Australians with access to some of the required manufacturing and packaging capabilities to deliver some of these very advanced ideas. So I think I'm going to start to move pretty quickly. And the last part of the talk is just to round it out with a bit of perspective on the New South Wales Smart Sensing Network and a bit of a perspective on the Jericho Smart Sensing Lab. Well, as Hugh spoke to, going back probably 16 years, we were talking to Mary, had known Mary for 25, 30 years. Turns out Justin Gooding, University of New South Wales, also knew Mary. To cut a long story short, we got together with Mary, proposed a pilot project to promote some sensor capability that addressed some very specific challenges. They were being played out in the media. And as you spoke to, koala tracking, we had then the Hunter Valley corridor coal issues that were playing out. We had some challenges that probably still play out in the media associated with PFOS, PFAS around Williamstown. And to cut a long story short, born was the idea of a New South Wales government-sponsored innovation network to bring together universities in New South Wales and in the ACT, it turns out, to collaborate, to interface with government industry, to accelerate smart sensor capability into solutions that address those real-world problems and at the same time contribute to our industry. I want to acknowledge that Hugh has been a great champion and mentor. And noting that Hugh was here this morning, I rapidly found the best photo I could find. And there we are with Susan Pond at an event, I think probably 4 years ago, downstairs, I believe. And I do want to acknowledge Hugh's mentorship and support for the New South Wales Smart Sensing Network. New South Wales Smart Sensing Network operating model is pretty simple. We bring together smart sensing expertise from leading New South Wales universities to develop interdisciplinary solutions to complex challenges across all of the verticals of society, relevant to your world's natural hazards, your health, the environment, agriculture, and we work across academia, industry and government. And I guess we've done a lot of good things over the last 9 years and probably running out of time, but just to call out one significant achievement was the work that we led with the water utility stakeholders. It addressed a real-world problem in terms of leaking water pipes. So 10% of our water leaks out of pipes. Who knew that? This is a global challenge. The water loss itself is probably not as damaging as the reputational infrastructure damage associated with catastrophic failure. To cut a long story short, we brought together a consortium of universities to collaborate with the water utility stakeholders to bring smart sensor capability across quantum sensors, LiDAR, acoustic sensors, and we provided Sydney Water and other water utilities capability that is adding to their bottom line, reducing reputational risk, providing more resilient infrastructure. So that's a great story. You can read more about it on our website. We have a broader role across a whole range of key areas of society, just drawing attention to natural hazards. As we grappled with bushfires, New South Wales Smart Sensing Network was out there leading the conversation, influencing how we respond to that threat as we are confronted by floods, accelerated arguably by climate change. New South Wales Smart Sensing Network has been out there leading the conversation on that front. And as we think about our national security, Jericho Smart Sensing Lab is out there. And the last thing I'll say on this slide is, as it relates to our national productivity, our economy, we are out there leading conversations around how to grow our industrial base and how to strengthen our manufacturing and how to create a more innovative ecosystem. So Hugh, in the last 3 minutes, if it's okay, I just want to give a bit of a round out on one other project that I can't say too much about. I am incredibly proud of this work and the team that supports this important project that has been sponsored by the Royal Australian Air Force since 2019, the Jericho Smart Sensing Lab. Let me give you a glimpse. I don't need to, because the public, the media is telling you every day why this matters. Richard Marles has been quite direct in his recent update. The National Defence Strategy is quite explicit about why this is important. And let me just quote from that document: "We have entered a more dangerous and unpredictable era, characterised by a more overt struggle amongst states where thresholds against the use of force are being eroded. Technological advancement and the changing character of war, including advances in AI and autonomous systems, are absolutely vital to our national security." So this project was launched in 2019. It is characterised as official sensitive, which means I can only disclose on a needs-to-know basis, and I'm not confident that everyone in the room falls into that category. There is no website. We do not publish, but we do great work, and our mission is to accelerate sovereign capability and advanced sensing. This is a photo from the launch, and I'm looking pretty handsome. on that day with my colleagues walking down the corridor of the Sydney Nanoscience Hub as we promoted that exciting project. Now, the last slide, I'll just sort of speak to what is really unique to this program is how we work with those stakeholders. And this is quite a trailblazing approach in science and innovation because we bring science and design together. So what that means is that we engage operators, we engage end users. We are explicitly committed to understanding the unmet need in terms of our national security, and we innovate according to those principles. We have a vertically integrated team that brings capability across those key areas, anchored in photonic science, and we use that design framework to ensure that the art of the possible, the great ideas that sit in my lab, are considered together with end user impact. That's all I'll say. Come up to me afterwards if you want me to elaborate. But the last sort of infographic is just to kind of give you that Australian context. This is really important. We're a big country. We're surrounded by a lot of ocean. And there's a lot of complicated stuff happening to the north of Australia. Last information is just a great little snapshot from one of my teams. Gives you a bit of a glimpse of some of the fun stuff we do where we put our sensors up to 110,000 feet. Again, I'll let your imagination run. Thank you, Hugh, and I'm happy to take some questions.
So people want to put their hands up for questions, but I might kick off with one. I do feel increasingly that there is a real sweet spot in Australia around the development and commercialisation of quantum sensing technologies, not just PNT, and I mean there have been some great successes, we have some great companies, but also in areas like quantum radar receivers and all these sorts of things. I just want to get your feeling as to, you know, should we be doing that sort of stuff?
Well, quantum sensing, I mean, I think I agree, and it's fair to say, you know, you've got the quantum world, and a part of the quantum world is quantum sensing, quantum compute, quantum sensing, and you're right, Australia has probably 3 or 4, maybe 5 really strong research groups, including companies doing great work on quantum sensing. Quantum sensor essentially, as I interpret it, can and is a device that measures exquisitely gravity or magnetic field. Quantum sensor is great if you want to map the underground. And the work we did with Sydney Water that I alluded to actually included some great work from ANU on quantum sensing, using an atom interferometer to exquisitely measure the local gravity that allows you to infer whether a water pipe is leaking or not. Right, you've taken it to quantum radar. I'm not sure if I believe in quantum radar, Hugh.
I've seen one.
Have you? Yeah, well, people I talk to, who have probably talked to people you've talked to.
But it's need to know, so I can't tell you.
Yeah. So, look, there's a lot of good stuff playing it. You've got to be, not that I would ever suggest that you're in this category, but you've got to be careful what plays out. Thinking of that recent incident in the Middle East where supposedly a quantum sensor remotely detected the heartbeat of a pilot. Yep. Absolutely fake news.
All right, questions from the floor. Sorry, go for it. Yep.
Yeah, thanks, Ben. Really enjoyed your presentation. Being a technician in my past life, driving optical fibers, so it was very relevant and reminiscence of my some work. But I was just wondering, how does CSIRO play any role in quantum computing or photonics, or is there any research being done there?
I might broaden it and say, where are the key research groups in Australia in photonics other than you?
Yeah, right. So, yeah, we have across Australia, this is not your question, but photonics is a national strength. The Centre of Excellence that I led, those universities, ANU, Macquarie, UTS, Swinburne, RMIT, are still powerhouses, and I would expand by saying Adelaide University, Melbourne University, UQ, all have great photonics. So we have a fantastic, and it's for historical reasons. It's basically traces back to radar, Second World War, innovation, fibre optics. You can track down to a few individual academics, but Australia and New Zealand has a vibrant photonics and quantum technology ecosystem. CSIRO is part of that. CSIRO has a quantum flagship. I guess the Quantum Australia people engage CSIRO. They have some photonics research. Probably, I can't point to exactly what CSIRO is doing in the photonics exactly right now, but I think they're relevant to the national ecosystem for sure.
Over there. Sorry. Sorry, do we have one over there to start with? I apologise. Go for it.
I just have a fun question. I just have a fun question because of 4 decades ago, I was a computing student as well. Around before that. So, I have read the novel from George Orwell, 1984.
Yes.
Yeah, which is very funny and exciting, and so quite, yeah. So today we're all bothered by the personal computer. I keep interrupting with my talking. And so with the photonics, are we going to get to the TV in the 1984 that it's been watching the house, and that this will be in the personal level? How soon would that be?
So how many smart sensors do you want in your house is the question.
No, I mean, in personally looking at me doing things, I'm breathing, I'm going here and there. So exciting. I mean, it's good for health.
100% agree. Look, there are great ethical questions around privacy and agency. Look, Hugh, for most of the time I've known Hugh, did not have a smartphone.
Still don't.
Okay, so riddle me that one, Batman. I mean, he has no smartphone.
Because I know too much.
Right, so I have a smartphone, but maybe that's what I should do to jump. Look, it's a great question. It's a great conversation. You have agency. You're empowered to decide on what sensors you want in your phone, in your house, in your world. Right, you know, there are extremes. There are countries that go way too far in terms of monitoring our lives. Right. What lives, what world, what rules do we want? Great question. Great conversation to have.
Yeah. And it's not a conversation we're having, actually.
Yeah, no, it's a good one.
Sorry, over here.
Yeah, look, you're part of AUKUS, you're part of Five Eyes, Critical Defence Centres of Excellence. My question is around how do you commercialise and how do you keep the commercialisation in Australia? Because I can hark back 35 years ago to a Star Wars project of Ronald Reagan, which was high altitude aerial radar, HARP, or Jindalee over radar. Over horizon radar as we knew it in the days. And it was a brilliant initiative by the Labor government at the time, Hawke and Keating, brilliantly exercised, except at the end of it, we lost the IP. Telstra lost 1.4 billion, because I worked for Telstra at the time on the project, or not on the project, but a commercial body that managed that area. How do we get around those problems? How do we keep the technology? How do we make ourselves a lucky country with technology?
Let's not.
Again.
Yeah, great question. Let's not let that happen again. So, yeah, I think lots of things. We're more sophisticated than we were. We still need to grow our industrial base and get our universities to be more agile and have more support from venture capital to create that ecosystem that we need. But it's the right question, and we grapple with it because there is an asymmetry, as you've alluded to. We need to collaborate and cooperate with our AUKUS partners, and we are, but we also need to have our industrial base and sovereignty capability. There's no easy answer, but it's the right question, and I'll just say we're more sophisticated than we were.
I think there's something else that's worth saying as well, that we are at that juncture point in areas like quantum. You know, we have, a number of very large quantum companies which are grown here. I think we struggle when it comes to scaling because we just don't have the funding here in the private venture funding to scale to large companies. But I do think things are changing. So we're in a better position, I think, today with quantum perhaps than we were with, let's say, photovoltaics 30, 40 years ago. But we're not there yet, and you're in the right thing because actually the next talk we have is of a successful company. I'll come to that in a minute. So Can we get a selfie? Really sorry. No, can we get a selfie? You ready, everyone? Everyone, go.
Okay.
Okay, good. All right. Thank you very much, Ben. Let me give you that. A great talk, everything else. Our next talk will be on Wednesday, the 17th of June, and we are very fortunate to have, I'm going to get the name wrong, Jeka. We speak of her. She's Jekaterina Vektorova, and she is a successful founder of a semiconductor company in Sydney, which I think last month raised $50 million. So it is one of these burgeoning industries, people may not be aware, where we genuinely have a growing semiconductor industry and quantum industry in Australia. And it's great to also have a female founder of a deep tech company like that as well. So hopefully you'll all be here for that talk on the 17th. Look forward to seeing you again then. Thank you.